All right, so we're dealing with a quantum system here, and we're talking about a transition between different levels by absorbing photons. And what are we trying to figure out here? What's our goal in this one? Yeah, we want to figure out, are we talking about larger or smaller energy gaps? And I think in this case, it's very useful to visualize the energy levels as sort of a ladder going up from the lowest energy up to higher and higher levels of energy. So if we got this, essentially just an energy axis, so like a one-dimensional graph, instead of having like energy and position, we're looking at just energy. And there are various different levels energy is allowed to be. So we've got some lowest possible energy, the ground state. And we don't even know what these values are, but some lowest possible energy that the system can have. And then the next energy it can have, and the next one, and the next one. And maybe these gaps are getting bigger and bigger, or smaller and smaller, or maybe even staying the same size. We don't know yet, but that's what we're trying to find out. So let's say this is energy level 1, energy level 2, energy level 3, and energy level 4. And we know that if you start at a certain energy level and you want to transition up to the next energy level, like let's say you start at energy level 2 and you want to transition to energy level 3, that's going to cost some delta energy. And how would you add energy to a quantum system like this? What's it gaining energy from? If you have some atom or something and you want it to gain energy, how do you give it energy? Or what mechanism do we use to transfer energy to or from a quantum system? Yeah, if you want it to gain energy, you shoot a photon at it. In order for it to lose energy, you would have to emit a photon. In this case, to gain energy, it's got to gain a photon. It's got to absorb a photon that's shot at it. So presumably the change in energy, the energy it gains, is the energy of the photon. In general, the change in energy of the system is either plus the energy of the photon or minus the energy of the photon, depending on whether we're gaining energy by absorbing a photon or losing energy by emitting a photon. But in general, we would say the change in energy of the system is plus or minus energy of one photon, with the plus or minus determined by whether it's absorbing or emitting a photon, gaining or losing the energy. But E photon should always be treated as a positive value. And you have a formula for how much energy a photon has in terms of its wavelength, which is what's described here. How does the energy of a photon relate to the wavelength of the light? The general idea there is that the energy of the photon is proportional to the frequency that is light with higher frequency, that is more towards the blue end of the spectrum, is going to have more energy per photon. And light with lower frequency, more towards the red end of the spectrum, is going to be less energy per photon. And proportional to frequency just means it's going to be some constant times frequency. That constant is specifically Planck's constant. So the energy of one photon is going to be Planck's constant times the frequency of the light. But think back to the basics of waves. What's another way you can write frequency in terms of wavelength? How do frequency and wavelength relate to each other? Yeah, frequency is the same as speed over wavelength. So we can write this as Planck's constant times speed over wavelength. And since we're specifically talking about light, speed is going to be c, the speed of light. So we can say energy of one photon is Planck's constant times speed of light over lambda. And Planck's constant and speed of light show up multiplied together like this often enough that we often just treat that hc as one single constant. So hc we can just treat as a constant divided by the wavelength tells you the energy of the photon. Which means energy of a photon is inversely proportional to wavelength. Larger wavelength means less energy. Shorter wavelength means more energy per photon. And keep in mind, this is all per photon. It's not telling you about the total energy of a beam of light. It's telling you about how that energy is split up into individual packets called photons. So one photon of light has an amount of energy that's inversely proportional to the wavelength of that light. Any questions on that so far? So if we're comparing these two gaps on the energy axis, each one of those can be thought of as delta energy of the system equals energy of one photon. But the energy of the photon can be written as hc over lambda. And which one of these involves a larger lambda? A larger wavelength of light. According to the first paragraph.
2 to 3.
Yeah, from 2 to 3, we've got a larger wavelength. From 3 to 4, it's only 2/3 that much, a smaller wavelength. So from 2 to 3, we've got a large wavelength versus from 3 to 4, we've got a smaller wavelength. What does that tell you about the delta energy involved? A larger wavelength would lead to what?
A smaller change in E.
Right. A large wavelength corresponds to only a little bit of energy per photon, and therefore a smaller energy gap. Whereas a smaller wavelength corresponds to a larger energy per photon, and therefore a larger energy gap. So it looks like from 2 to 3 is smaller energy gap, from 3 to 4 is a larger energy gap. So that suggests that as we go up the scale, as we go up this ladder, we start with small energy gaps, and then we're getting to larger and larger energy gaps. And then presumably E4 to E5 would be even larger. So something like that. Smaller gap and then getting larger and larger and larger further apart as we go further up the scale. So the higher the energy is already, the more energy it's going to take to jump up to the next level. Whereas if you're low down, it's going to take only a small gap to get to the next level. So this is going to behave more like the particle in a box model with these small gaps at the bottom and larger gaps as you go further up, as opposed to the hydrogen-like atom model has larger gaps at the bottom and then smaller and smaller and smaller gaps the further up you go. Any questions on that so far? And it looks like we then want to figure out the transition from 2 to 4. In part B, it's asking from 4, well, I guess from 4 down to 2. We're losing energy by emitting a photon. So let's say we want to drop from 4 down to 2, and we're emitting a photon. In that case, we can say the energy of the photon equals the absolute value of the energy lost from 4 to 2. So energy of the photon emitted is going to be absolute value of energy lost from 4 to 2. And we know about the energy from 2 to 3 and from 3 to 4. So how can we combine those to get the total energy lost from 4 down to 2?
We just combine the delta E for both of them, but when we move down, it just lose that much of energy. So when we take the absolute value of it, it should be the same.
Yeah. And yeah, we should be able to just add those absolute values. So energy gained from 2 to 3 plus energy gained from 3 to 4 is the total energy gain. And in terms of absolute value, that's the same as the total energy loss. So we should be able to just add energy gained from 2 to 3 plus energy gained from 3 to 4. And each one of those individually can be written as HC over lambda. So we've got HC over lambda 2, 3, which we're just calling lambda sub 0, plus HC over lambda from 3 to 4, which is only 2/3 that much. So if we add those together, then that will tell us the energy lost from 4 all the way down to 2. Any questions on that so far? And because if we're talking about the wavelength from that works from 3 to 4, it specifically tells us that wavelength is 2/3 of lambda naught. So you've got HC over lambda from 2 to 3, which we're just calling lambda naught, and also HC over lambda from 3 to 4, which we're specifically told is 2/3 of that lambda naught, 2/3 of that same wavelength. And 2/3 in the denominator, because ideally we want the denominators to be the same so we can actually add these together. 2/3 in the denominator is equivalent to what fraction in the numerator?
3/2.
Right. So we could rewrite this as HC over lambda naught plus 3/2 times HC over lambda naught. Now we've got the same denominator, so we can just combine those and get HC plus 3/2 HC, that's 5/2 times HC over lambda naught. So the energy of the photon that is emitted, if you drop from 4 all the way to 2, the energy of that one big photon would be 5/2 times HC over lambda naught. And presumably that's the energy. But we're not looking for energy. What are we actually looking for here?
Wavelength.
Right. And we can use the same formula. We can set this energy equal to HC over the new wavelength. Let's say HC over lambda 1. So if we set this equal to HC over lambda 1, let's say lambda 1 is the photon emitted as we go from 4 all the way down to 2, we should now be able to solve for lambda 1. And how would we do that? How would we isolate lambda 1 here?
Lambda 1 equal HC over E photon.
Sorry, what was that?
Oh, sorry. Lambda 1 equal HC over E photon.
Well, we don't really even need to use E photon here. We can just use the fact that these two things are equal. Ideally, we want to find lambda 1 in terms of lambda 0. So in this equation, how would you isolate lambda 1?
Would you divide both sides by HC?
Yeah, I think that'd be a good start. And since we've got HC on both sides in the numerator, dividing by HC is just going to cancel that out. So that means we're left with 5/2 times, I guess we're left with just 1 over lambda naught equals 1 over lambda 1. And then since lambda 1 is just in the denominator here, how do we get lambda 1 back in the numerator?
Take the inverse of both sides.
Yeah, if we take the inverse of both sides, we get lambda 1. And then what do we have on the left side if we take the inverse?
2/5.
Right, specifically 2/5 times lambda naught. So that tells us the wavelength of the emitted photon from, as we drop from E4 all the way down to E2, in terms of the original wavelength. The emitted photon has a wavelength, as we drop from 4 all the way to 2, the emitted photon has a wavelength that's 2/5 of the original wavelength we were talking about that takes us from 2 to 3. And again, this corresponds to the idea that a larger amount of energy, a larger energy gap, corresponds to a smaller wavelength, because those should be inversely proportional. Any other questions on that?
For B, they call, can I assume that the one that you call lambda 1 is lambda 4 too, that they call in question B?
Yeah, I guess that is the notation they're using. Lambda 4 too. I didn't see that, so I was just making up a new variable for it. But yeah, the wavelength we're talking about for the emitted photon as the system drops from energy level 4 down to energy level 2. That's the wavelength we're looking for here. And that turns out to be 2/5 of the wavelength that would take us from energy level 2 to energy level 3. Any other questions on that? And then what are we dealing with in part C? We've got a couple of double slit experiments, and it looks like part C is not actually using the quantum stuff at all. Part C is a completely different problem. It's just using lambda naught and 2/3 lambda naught as the wavelengths we're talking about. So ignoring parts A and B entirely, ignoring all the quantum stuff, we've got a double slit experiment that's using wavelength lambda naught, and another double slit experiment that's using wavelength 2/3 lambda naught, 2/3 as much wavelength. And what's the same about both of these experiments? What are we using the same in both of the experiments? Well, what does the text tell us is the same in both experiments?
The interference is the same.
Yeah, we're getting the same resulting interference pattern. That is and presumably we're going to get an interference pattern of like bright spot, dark spot, bright spot, dark spot, bright spot, dark spot, spaced out the same amount. So in both setups, we get the same distance from bright spot to bright spot, which we usually call delta Y. So they both have the same delta Y between bright spots. So when we write out the equations, we can use that as a substitution or set the delta Y's equal to each other. What else is the same about these setups? What other values are going to be important in the double slit experiment equations? Actually, do you have an equation for the double slit experiment? I would say these are two different sources. We've got one experiment that's using wavelength lambda naught for both slits, and another experiment that's using wavelength 2/3 lambda naught for both slits. So these are two completely different double slit experiments. But what is the same about them? What other numerical value are we told is the same about both of the slits? Or both of the double slit setups?
Small d.
Yeah, little d, the distance between slits. In both of those, the two slits are 0.02 millimeters apart. So in both of those, we've got little d equals 0.02 millimeters. And same thing over here, little d equals 0.02 millimeters. So we're using the same pair of slits for both of them, or at least this identical pairs of slits. And different wavelengths, but we still get the same physical distance between bright spots. And how is that possible? What else could be different that would lead to the same difference between bright spots, even though we're using different wavelengths? Phase constant doesn't matter because we're talking about a single light source emitting light on two slits, hitting both at the same time, so there's no phase difference. And then separately, we've got a different light source that's also hitting both slits at the same time, so that also has no phase difference. So we don't need to worry about phase difference here. And in fact, even if there was a phase difference, both of these would have the same phase difference, so that wouldn't make any difference between them. But what else about the setup determines how far apart the bright spots are?
The big D.
Sorry, what was that?
The distance between the screen and the source.
Yeah, from the source and the slits to the screen, usually written as capital D. And it tells us that in the first experiment, we're using capital D equals 80 centimeters, the distance to the screen. In the second experiment, we don't know. We're trying to figure out what distance to the screen we will have to use to make these still have the same delta Y between bright spots. So we have different wavelengths, same distance between slits, but different distance to the screen that's supposed to result in the same delta Y between bright spots. And you have an equation you could use for delta Y, or that relates delta Y to all these other variables. What equation would tie all those together? Do you have an equation for this? Was there an equation you dealt with in lecture or discussion lab for figuring out how high the bright spots are or how far apart they are? Let's backtrack to that then. If we're dealing with a double slit setup, let's say we've got the wall with a narrow slit in it, and then another narrow slit. Something like that. And then we have another wall somewhere further off. So we'd say the distance between the walls is what we're calling capital D. Which in this case is 80 centimeters. And then lowercase d is the distance between the two slits, which is presumably much, much, much smaller. And if we're talking about, if we look at the light that spreads out here, we're going to end up with a pattern of bright spots and dark spots. Presumably, you're going to get a bright spot directly across from the center. And then alternating pattern of bright, dark, bright, dark, bright, dark. And then below also a symmetric pattern of bright, dark, bright, dark. And we usually call the central bright spot, we associate n values with this. N equals 0 is the central bright spot. Then n equals 1 is the next one up. And then n equals 2. And we're going to get the exact same pattern underneath. If we need to, we can refer to those as negative n values. So n equals -1, n equals -2, and so on. And the center is going to be a bright spot specifically because if we draw out the paths light is taking from the top slit to this location, I guess I should make this more symmetric. Top slit to this location and bottom slit to this location. Let me actually correct that. To get to a spot exactly in the center. Why would that center be a bright spot? Why should we expect the spot directly in the center to be bright, constructive interference? What do we know about both of these path lengths?
Because it has the same distance from the slit to the screen.
Yeah, from the top slit to this location and from the bottom slit to this location, right? Equal path length, same distance. Therefore, there's no delta path length, no delta x. And there's no other differences. There's no phase shift difference because the light is coming from the same source. So this location has 0 total phase difference. And therefore, we get a bright spot. The waves are identical. They're traveling the same distance. They have no other differences. So we get constructive interference. If we take a look at some other location, let's say if we analyze the paths from each slit to this location, that's going to be a bright spot under what circumstances? What has to be true for that location to be a bright spot?
They have to interfere constructively.
Right, we need constructive interference. So what has to be true for that to be constructive interference?
The phase change needs to be like in sync. Like, like even.
Sorry, what was that?
Like even.
Even what?
Like 2 pi or like 4 pi or.
Yeah, so an even multiple of pi, which tells you, well, what's special about 2 pi? What is 2 pi? What does that mean, though? What's special about 2 pi specifically? But why 2
think it
pi?
re-
Why is 2 pi the special value and not like 5 pi or 7.5 pi or square root of 37?
It relates back to the trig circle where 2 pi is a full rotation. So when you add 2 pi to something, you're not changing the value since it's a complete rotation.
Exactly. We want a full, in terms of the angle, one full rotation is 2 pi radians. And since we're using the rotation as a metaphor for a cycle of a wave, 2 pi represents one full cycle. So we don't really even need to think of this in terms of 2 pi or in terms of radians at all. We could think of this as, to be a bright spot, we need a whole number of cycles. An even multiple of pi just means a whole number of cycles. A whole number of cycles offset. So to get a bright spot, we need the total phase difference to be a whole number of cycles. In this case, since there's no phase shift difference, the only difference is coming from the difference in path length. In other words, the difference in path length has to be a whole number of wavelengths. Delta x, the difference between these two distances, has to be a whole number of wavelengths. I put the lambda here. No, lambda, there's a whole number of wavelengths, because one wavelength is one full cycle worth of distance. If the, again, assuming there's no other difference, assuming that there's no difference in time, no difference in phase shift, if the only difference between these two waves is how far they travel, because one of the paths is a little bit longer than the other. If the little bit longer, the difference in path length is a whole number of wavelengths of that color, then we get a bright spot. That is constructive interference. Any questions on that so far? And do you have a formula for what delta x is in this particular case? Because so far, delta x equals n times lambda. This is true in general. For any interference situation where path length is the only difference, path length difference equals a whole number times wavelength will always get you constructive interference. But what about in this particular situation? Do you have an equation for, or a formula for path length difference related to the distance between slits? Yeah, sine theta would be delta x over d, so delta x is d sine theta. In general, in the double slit situation, geometry gives us that delta x equals d times sine of the angle, specifically the angle of elevation to the point we care about. So we could write this as, if we put this all together, we get n times lambda has to equal d times sine of the angle, usually written as theta. So that would be our usual equation for getting a bright spot on this pattern. Any questions on that so far?
What is the angle again?
The angle would be the angle of elevation between, if you take a horizontal, so like from the slits out to the central bright spot, and then a diagonal from the slits up to the location you care about. The angle we care about is that angle of elevation. So that's the angle we're talking about here, sine of that angle. Any other questions on that so far? However, we don't really want to relate this n lambda and d to the angle, because the angle isn't really something we care about. The angle is going to be different between these two experiments anyway, because we're moving the screen further out or closer in. What we really care about is the distance between the splits, the delta y. So how would you relate the sine of the angle to the delta y? Like the actual physical distance between the slits on the wall, like this distance here. Can you see a geometric way to relate that to sine theta? Yeah, if we make that comparison, the sine theta, or the d sine theta is going to be very closely related to this. Specifically, we can set up the relationship that if we draw out another triangle, let's say we draw out this triangle.
Is it tangent of theta equal delta y over d?
Yeah, because if we take a look at D here, D is that, a capital D is that distance between the slits and the wall. So if we're considering this angle, tangent of that angle would be opposite over adjacent, delta y over D. So we can say that tangent of the angle is delta y over D. That's not quite the same as sine of the angle, but it's going to be very, very close. For small angles, sine of the angle and tangent of the angle are almost the same anyway. Because sine of the angle would be delta y over the hypotenuse. But if the angle is very narrow, the hypotenuse and that horizontal leg are almost the same distance anyway. So we can say this is equal to approximately sine of the angle. That's called the small angle approximation. That for small angles, angles close to 0 radians, sine of the angle and tangent of the angle and the angle itself, if it's measured in radians, are all pretty close to the same value. Like if you got an angle whose radian measure is 0.01, the sine of that angle will also be pretty close to 0.01, and the tangent of that angle will be pretty close to 0.01 as well. They'll all be about the same value. So we can make that replacement. We can say that n times lambda equals approximately d times sine of the angle. No, sorry, n times lambda is exactly d times sine of the angle, but that's approximately equal to d times tangent of the angle. So n times lambda is approximately d times tangent of the angle. And then tangent of the angle can be rewritten as delta y over d. So d times little d times delta y over big D. So we can use this as a very useful approximation that now relies entirely on distances and doesn't care about angles at all. So that means that if we wanted to figure out, for instance, the height of the nth bright spot, because keep in mind, this is just talking about bright spots. If we solve for delta y, we can just multiply by big D and divide by little d. So n times wavelength times big D divided by little d. So this formula tells us the height of the nth bright spot. Any questions on that so far?
Can you repeat what you just said? The formula is what?
This will tell us the height as measured from the center of the nth bright spot.
And
So like if you wanted to find
0.
the height of the, sorry, what was that?
So the distance difference between the two bright spots.
Well, specifically the height difference between the center and the nth bright spot. So if you wanted to find like the height of the 5th bright spot as measured from the center, you'd use 5 for n. N is just keeping track of which bright spot we're talking about, with n equals 0 meaning the center, n equal 1 meaning the next bright spot away from the center, n equals 2 meaning the next bright spot beyond that, and so on.
So exactly from the center bright spot to whatever bright spot we are.
Right. Alternatively, if you replace n with 1, that'll just tell us the distance from the center to the first bright spot. And that should be pretty close to the distance from the first bright spot to the second bright spot and from the second to the third and so on. So if we just replace n with 1, lambda times big D over little d tells us the difference between adjacent bright spots. And realistically, they're not all going to be exactly the same distance. The distances get a little bit more spread out as you get further from the center. But if we're talking about close to the center, using the small angle approximation, the bright spots will be evenly spaced, or very close to evenly spaced. And lambda times big D over little d tells you the distance between adjacent bright spots. And since we're assuming that, or since we're specifically told that both of these experiments give you the same pattern, same interference pattern, That means they'll have the same difference between bright spots. So what can we do with this formula? Well, we've already isolated delta y here, but what do we know about delta y in experiment 1 and delta y in experiment 2?
They're the same.
They're the same. So what can we, if we wrote out this formula for experiment 1 and wrote out this formula again for experiment 2, what could we do with those two formulas?
So we set their delta y equal, and then we solve for.
Yeah, exactly. We could set those equal to each other. So for experiment 1, we've got lambda naught times big D, 80 centimeters, divided by little d, 0.02 millimeters. For experiment 2, and we can set these equal to each other. For experiment 2, the wavelength is 2/3 times lambda naught. The distance from slits to wall is unknown, so that's an unknown big D, divided by the same little d, the same 0.02 millimeters. And at this point, I think we should be able to solve for big D. First of all, what can we cancel out here? What could we just divide out completely?
Wait,
Lambda naught.
Sorry, what was that?
0.02.
Yeah, they both have a divided by 0.02 millimeters, so we can multiply both sides by 0.02 millimeters to cancel that out, which actually tells us we didn't even need to know this 0.02 millimeters here. All we needed to know is it's the same slit separation. And also, what else shows up on both sides of the equation?
The original wavelength.
Yeah, we've got a lambda naught on both sides. On the right side, it's being multiplied by 2/3, but it's still 2/3 times the same variable. So we could divide both sides by lambda naught, leaving just the 2/3. So it looks like all that remains is 80 centimeters equals 2/3 times d, the distance from the slits to the wall. And then what could we do? How do we get rid of that 2/3?
Multiply each side by 3/2.
Yeah, so d equals 3/2 times 80 centimeters. In other words, 120 centimeters. So that has to be the distance from the slits to the wall in experiment 2 in order to make the interference patterns match up precisely. Any other questions on that?
Can I have a question? So going back a little bit to your double slit setup, you said that the N0, it's the bright spot, right? And then the N equal 1, is that also a bright spot?
Yeah, all of the whole number values of n will lead to identical bright spots.
Okay, gotcha.
And then the spots halfway in between would be dark spots.
Okay.
And one way you could find those dark spots, not the only way, but one way to find the dark spots would be to use the same equation, but instead of n being a whole number, you would use something and a half for n. Like for instance, if you use 1.5 for n, you'll get the location of the dark spot that's halfway between n equals 1 and n equals 2. Any other questions on that? All right, then I will see you next time.